Let's go back to our lab 1 and think about more about BFS breadth first search. When I have a root, there's a root node. Then if I have branch factor B, if B is 3, each time I'm going to have 3 children or 3 neighbors. So if I have a depth 0, this one is depth 0, then depth 1. If I have a depth 0, I'm going to have only one node. If I have depth 2, depth 1, I'm going to have now 1 plus 3, so I'm going to have 3 more. Now let's think about in depth 2, each one will have 3 children. So in depth 2, I'm going to add 9 more. In depth 2. Then in depth 3, here 9 more, 9 more, then 9 more. So in depth 3, I'm going to have 999, so 27 more. How about in depth 4? Now I'm going to have, oh, it's really hard, 3 to the 4th, 81 nodes. So I can see b to the 0th power if it's depth 1. Then whenever I add more depths, b to the 2nd power, b to the 0th power plus b to the 1st power. So 1 plus 3 plus 9 plus 27 plus b to the this power. Now let's think about what is b to the this power and compare to b to the 0th power to b to the d minus 1st power, d minus 1. Easiest one we can use is like a 2 to the like a depth is 10, 2 to the 10th power is 1 plus 2 plus 4 plus 2, 2 to the 9th power. The sum of all of them will be 1 less than 2 to the 10th power. Let's see. 4 is 1 more than 1 plus 2. 8 is 1 more than 1 plus 2 plus 4. 16 is 1 more than 1 plus 2 plus 4 plus 8. So 1 to 2 to the 9th is 2 to the 10th minus 1. Let's say 2 to the 10th as like a big X. That means big X plus big X minus 1. I can say this is 2x minus 1. Big O efficiency of 2x minus 1 is big O, big X. So this one's big O is b to the d. Now, let's go to the time efficiency of the BFS. Time efficiency. If you check the goal test, as soon as you take out from the frontier, so in the while loop, for example, then blah, 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 then you are going to pop it. Then if you have a goal test here, then if you have like a generate child, then blah, 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 blah. If a goal test is not inside of the for loop in your generate child, that means you are going to go 1 more depth. So you are going to go d plus 1 depth. Then space complexity. if you have b to the d's. But in explored set, you are gonna have one less when you go to the d, like d depth, because you are going to add explored in not here. You may add it here. If you add to the explored after you pop it, that means your explored will have one less because you are going to extend the children later. Then it's not in the explored yet. So in that case, frontier will go to big O b to the d's. Then explorer will go to big O d minus 1. B to the d minus 1 power. If our memory can work like a million things in milliseconds, this one is saying million is in 1 second. Million nodes you can do in 1 second. With this computer, if you have a depth 16 and branch factor is 10, you are going to explore 350 year to get reach to the depth, maximum depth of the graph. Okay, so this is not really good time-wise and also memory-wise. Exabyte, oh my gosh, right? So when branch factor is big, BFS is not good. So now let's say if B branch factor is big because it's exponential, BFS is not good. And also depth is big. BFS is not good. Even in this case, depth is only 10, 3 hours. If a branch factor is a 10. Now let's see here. DFS. DFS has M. M means maximum depth. So it's possible to be greater than the depth of the solution. When I have, like for example, like a tree, let's say like this. My goal is at here, but if I do the depth first search, it's going to go last one, last one, last one, last one. So even though the solution's depth is 2, I'm going to search up to like a maximum depth, for example, 0, 1, 2, 3, 4. In this case, the depth is 4. So I can search more than my solution's depth. That's what M represents. So time efficiency for the worst case is big O M, big O B to the branch factor to the M's power. While the breast first was finishing at B to the D's power, in the worst case, DFS is much bigger, B to the M's power. When we have a branch factor with 10 and depth is 2, we can just do explore this much. That means 1 plus 10 plus 100. 1 plus 10 plus 100. So about 111, like 110 if we do not count this one, the initial one. How about when depth is 4, zeros plus 10 to the first, plus 10 to the second, and 10 to the third, and 10 to the fourth, and worst case, oh, 10,000, 1,000, 100, 10, and 1. How much bigger? Ooh, too much. That's time efficiency. Space efficiency as average. If you see, if my goal is like so far here, if this is the new goal, it is searching only 1, 2, 3, 4, 5, 6. 6 nodes will be searched when the goal is in the blue with DFS. How about with BFS? I'm going to search 1, 2, 3, 4, 5, 6, 7. Actually, I'm going to search the last one too in the same level, generate child. So BFS will search like 1, 2, 3, 4, 5, 6, 7, 8 node. So in that case, BFS is worse. How about if the goal is somewhere closer to my DFS? How about new goal? In that case, much more different. So DFS has space efficiency. In the average case, branch factor times maximum depth will be the branch factor DFS space efficiency. So space-wise, DFS is good. The optimal means guarantee the shortest path, guarantee to find the shortest path. BFS guarantee the shortest path, but DFS is not guaranteeing the shortest path. To get this goal, actually, the DFS is going through all the way, then come back and go there. So it is possible it goes all the way then. If we do not allow the comeback, even we do not allow the comeback in the graph search, like DFS is possible to all the way around then finally get the goal. It is possible.